Hi everyone. Today we'll be discussing the reactor capacity of anaerobic reactors. This is a crucial operational parameter for all anaerobic reactors, but it is of particular importance for high-rate anaerobic reactors treating high-strength wastewater. It is noteworthy that overload conditions can cause suboptimal reactor performance and major upsets in all anaerobic reactors. Anaerobic reactors provide ideal conditions for methanogenic cultures to digest substrates, and the proper design of anaerobic reactors is of paramount importance. However, it is vital to understand that the biology carrying out complex biochemical reactions inside the anaerobic reactors performs the digestion function. So let us start by understanding the underlying biochemistry behind the anaerobic digestion process. Anaerobic digestion is a multi-step process in which many microbial groups work together in syntrophic relationships. Food processed by one trophic group in this complex environment is passed over to another trophic group that processes it further. The first step involved in anaerobic digestion is called hydrolysis. In this step, complex organic substrates are hydrolyzed into simple organic compounds. In the second step, the simple organic compounds are converted into long-chain fatty acids, and this step is called acidogenesis. In the third step of anaerobic digestion, the long-chain fatty acids are converted into acetate, hydrogen, and CO2 gases. This step is called acetogenesis. It is important to note that hydrogen and CO2 are produced throughout the first three degradation steps. In the final step of anaerobic digestion, acetic acid, hydrogen, and CO2 are converted into methane by two separate groups of methanogens called acetoclastic and hydrogenotrophic methanogens. There is a third group of methanogens that convert substrates such as methanol into methane gas, but this group of methanogens is typically considered to be lesser important than the acetoclastic and hydrogenotrophic methanogens in anaerobic digestion of waste materials. Approximately 70% of the produced methane typically comes through the acetic acid pathway, whereas the hydrogen-CO2 pathway produces the remaining 20 to 30% methane. Although the hydrogenotrophic pathway contributes a smaller fraction of methane, it is vital to degrade energetically challenging compounds such as propionic acid and butyric acid. We'll learn more about this in subsequent lecture videos. Both these pathways are critical for successful operation of anaerobic reactors fed with complex substrates. The methalotrophic pathway has been discovered recently, and it is supposed to be of less importance in anaerobic digestion environment due to its lower contribution to the total methane generated in the process. This makes the anaerobic digestion an extremely complex environment, as the first three steps of the process are carried out by bacteria, whereas the final step of the degradation process is carried out by methanogens that are genetically classified under the domain Archaea. The diagram here shows the phylogenetic tree of life. It is interesting to note that Archaea domain containing methanogens is branched closer to the eukaryotic domain, under which humans, plants, and other animals are classified. Hence, prominent scientists believe that archaea are genetically closer to humans than bacteria. This means successful digestion requires syntrophy between two genetically diverse domains of life. Moreover, the methanogenic archaea have stricter environmental requirements, like higher life forms, making the anaerobic digestion ecology sensitive to environmental challenges. In anaerobic reactors treating particulate materials such as farm waste or municipal green bin waste, often hydrolysis step is the rate-limiting step. On the other hand, in high-rate anaerobic reactors treating high-strength wastewater, methanogenic activity is the process bottleneck. Among all the trophic groups present in anaerobic reactors, acidogenic microbes that produce volatile fatty acids have the fastest growth rate. On the other hand, acid-consuming methanogens are known for their slow growth rates. This means all major process upsets and organic overload conditions manifest themselves in accumulation of organic acids in the reactor. For high-rate anaerobic reactors, it is critical to monitor food-to-mass ratios. A food to mass ratios of 0.3 pound COD per pound of microbial biomass per day is considered ideal. Some extremely high rate systems can handle substrates up to a food to mass ratio of 0.45, but a majority of systems work below this food to mass ratio number. At high food to mass ratios, systems may choose for non-filamentous acidoclastic methanogens such as methanosarcina, and such system may fail to grow successful granular biomass critical for high-rate anaerobic reactors. On the other hand, a reactor that is moderately loaded chooses slow-growing methanosera that thrives at low volatile fatty acid concentrations. And methanosera has filamentous morphology and is of vital importance in growing granular biomass. Moreover, a moderate food to mass ratio allows sufficient food transfer while preventing biogas buildup inside granules. As the produced methane must escape through the capillary channels present in the core of granular biomass. On the other hand, a higher food to mass ratio and overload conditions can cause the accumulation of VFAs, such as acidic and propionic acid, in high-rate anaerobic reactors, leading to process upsets. This rapid gas production can lead to active biomass loss from high-rate granular reactors. This concludes today's lecture on food to mass ratio, and I hope it gave you a brief introduction to why this ratio is so critical for the successful operation of anaerobic reactors. If you have any further questions about this topic, please feel free to reach out to us. Thank you so much for your attention, and I'll see you in the next video. Bye.